Homework 2C. Question number 1. Under what conditions are delta H, delta U identical for a reaction involving gas, liquid, or solid? So this question is actually asking you when can the reaction enthalpy, reaction internal energy are equal. R means reaction. So first let's start with the definition of enthalpy, which is U plus PV. So delta U H equals delta U plus delta PV. Delta H equals delta U if delta PV goes to 0. So when can this goes to 0? When the reaction only involves liquid or solids, because liquid solids, the volume doesn't change, so delta PV is 0. That gives you delta H equals delta U. Now if the reaction involves gas phase, then in this case the delta PV may not be 0, so delta PV, let's see what this is, should equals to PV of the product minus PV of the reactant. And if gas obeys ideal gas law, so that will be nRT of the product minus nRT of the reactants. Okay, most chemical reactions are under constant temperature. The reactant product should have the same temperature in that case, so that will be, the T is the same, so it's N of the product minus N of the number of moles of product minus number of moles of reactants times RT. Okay, and therefore you can write as delta N times RT. So delta N is the product number of moles minus reactant number of moles. So can delta H equals delta U? Yes, if delta N is 0. Okay, in other words, if the reactants, alright, if this is 0, if the reactants number of moles equals the product number of moles. For example, let's say you have 2A gas phase forms 1B plus 1C. So in this case, you have 2 moles gas phase, 1 more B, 1 more C. So the product also 2 moles. And therefore, delta N is 2 minus 2 is 0. So for this kind of reaction, the delta H should equals to delta U. Okay, here is delta H is the reaction enthalpy, reaction internal energy. They are equal because the reactants product are equal. So this equation is important. You need to remember that is the reaction enthalpy equals internal energy change for the reaction plus delta N times RT. Okay, so delta N is the number of moles from reactants changed to the product, how much the difference. And you are going to see this equation again in the last question. So question number 2 asks you, why is it valid to add the enthalpies of any sequence of reactions to obtain the enthalpy of the reaction, that is the sum of the individual reactions? So it asks you that in order to get delta H directly from reactants A to P, you actually can imagine the reaction go from another path, first to B, and then C, and then P, and the delta H should equals to the sum of all these steps. Okay, why is this valid? Okay, the reason is enthalpy is a state function. So if it's a state function, then as long as the reactants, the product are the same, so no matter how you go from A to P, okay, different path, they have the same delta H. Okay, and therefore delta H equals delta H1 plus delta H2 plus delta H3. Any path between the reactants and the products regardless of which intermediate products are involved, has the same value of delta H. Question 3. Use the tabulated values of enthalpy of combustion of benzene and the enthalpy of formation of carbon dioxide and water to determine the formation enthalpy for benzene. So this question is about the combustion of benzene. Let's first write the reaction for combustion of benzene, which is a complete oxidation to form water and the carbon dioxide. The enthalpy of combustion of benzene can be found from textbook, and assume you already get this number, which is negative 3,268 kilojoule per mole. Note that this chemical reaction is the combustion reaction, and therefore the reaction enthalpy for this reaction is negative 3,268 kilojoule per mole. Okay, and also the enthalpy of formation of CO2 and water can also be found from the textbook. And these are the numbers. It asks you to calculate the enthalpy of formation for the benzene. Oxygen is an element, and the formation of enthalpy is 0. So how is this enthalpy of formation of benzene is related to the reaction enthalpy? The equation is the reaction enthalpy is the formation enthalpy of the product minus reactants, which is the formation enthalpy of the CO2, water minus oxygen minus benzene. So plugging all the data, alright, so the only thing unknown in this equation is the formation enthalpy of benzene. So a simple mathematical modification gives you formation enthalpy of benzene equals the formation enthalpy of carbon dioxide, water minus combustion enthalpy of benzene. So plug in all the data, including the coefficient. So remember, you need to times 6, all right, and times 3, which is in this equation. Okay, also the oxygen is 0, so this is 0. So the answer is 49.6 kilojoule per mole. All right. So question number 4 asks you to calculate the reaction enthalpy and the reaction internal energy at 298.15 Kelvin for the following reactions. It gives you the table of formation enthalpy and the combustion enthalpy for different substances. First, let's start with question A. Write the reaction equation is the ammonia NO forms nitrogen gas and water. And to calculate reaction enthalpy, we need to find the formation enthalpy of the product and the reactants. So the product is ammonia, is water. So let's see, you have 2 water here. Because the reaction is a gas phase, so you choose this value times number 6. Okay, coefficient is 6. And nitrogen, this one should be 0. And ammonia is negative 45.9 times 4, and NO 91.3 times 6. All right, so the reaction enthalpy should be the product minus reactants, which equals first 0 because nitrogen elements 0, minus 6. Now you should minus, so why this is negative? You should add a product, and the reason negative because this number is negative. Okay, so it's negative. Now this is the product YU plus, and the reason is ammonia is negative. So if you minus negative, you get a positive number. All right, and NO is positive, so you minus the product. And the answer is negative 1,816 kilojoule per mole. Now next, in order to calculate delta U, you should remember the equation is delta H, reaction enthalpy, should equal to delta U, reaction internal energy, plus delta N times RT. Okay, now if you don't remember which one is left side, which one right side, you should remember this. H equals U plus PV. So delta H equals delta U plus delta PV is delta nRT. Okay, and therefore the delta U should equals to delta H minus delta N times RT. Now delta N in this question, let's calculate. For the reactants is 4 plus 6 is 10. The product 5 plus 6 is 11. So delta N is 11 minus 10 is positive 1. Okay, so the delta U equals delta H minus 1 times RT. That gives you 1,818 kilojoule per mole. And notice that the delta H and delta U are very close. Okay, if your calculation are orders of magnitude difference, then you might have a problem, made a mistake. Okay, so that's A. The other questions, B and C, should similarly, you should find the reactants product formation enthalpy and the product minus reactants. The only thing I want to mention is how do you calculate delta N. For question B, let's calculate delta N. And so the gas phase reactants is 2 plus 1, so it should be 3. And the product is 2. So it should be 2 product minus 3 is negative 1. Okay, so remember the delta N for B is negative 1 for B. Now for C, let's calculate. So reactants is 1, here is 1, so total is 2. And the product, note that this is a liquid. Okay, and therefore the delta N should be 0 minus 2 is negative 2. Delta N. Delta N for C is negative 2. Okay, because the product is liquid, liquid is not counted, only in the gas phase. Liquid solid doesn't change volume, so delta PV is 0. You only count the gas phase. Okay, so B is negative 1 and C is negative 2. And so let's see. For B is minus delta N, and because it's negative 1, so minus 1 equal minus negative becomes positive. Similarly here, minus negative 2 becomes positive 2. Okay. In question 5, at 298 Kelvin, the standard reaction enthalpy for the following reaction can be calculated from standard enthalpy of formation. If we know the heat capacities for the reactants and the product, calculate reaction enthalpy at 125 Celsius. So first, let's calculate reaction enthalpy at 298 Kelvin using the standard enthalpy of formation. The equation is the formation enthalpy of product minus reactants. In this reaction, carbon and hydrogen are elements, so they are zeros. And you can find the values for CO and water, and the calculated value is 131.3 kilojoule per mole. Now, we have 298 Kelvin reaction enthalpy. We want to calculate 125 Celsius, and the equation is to calculate 125 Celsius or 398 Kelvin. You use 298 Kelvin reaction enthalpy plus a temperature correction. Now, if the heat capacities are constant as these questions indicate, then you simply add delta Cp times delta T instead of using integration. So the delta Cp is calculated by the heat capacity of product minus heat capacity of the reactants. In this reaction, the coefficients are all 1. Okay, and that's why here they are all 1. Now, if the heat capacities are not 1, you have to times the coefficient to calculate the delta Cp. Delta T is the final temperature minus initial, which is 398 minus 298, and that gives you 100 Kelvin. One more thing I want you to pay attention is the unit. The reaction enthalpy unit always a kilojoule. That's the delta H. But the heat capacity is joule. Okay, it's joule. So in order to add this together, you must times 0.0001, okay, to change to kilojoule, so that they are consistent. Okay.